Welcome back. We'll continue with our discussion about appearance of the multiplicity pattern when the group of equivalent spins are coupled to a different spin. You may please remember in the last class I showed you what happened to a CH2 proton coupled to a CH proton. In this case, these two CH2 protons are equivalent and splits the CH proton into a triplet. I showed you diagrammatically by a stick plot how we get a triplet for CH proton. Where since two couplings of CH2 two protons coupled to third proton CH proton, because the couplings are identical, two central lines overlap and we get 1:2:1 triplet for CH proton. On the other hand, if you look at the CH2 group, it is coupled to CH proton, that will be a doublet. So the total spectrum of a CH group coupled to CH2 group in an NMR spectrum will be a doublet and a triplet. Triplet is for CH proton, doublet is for CH2 proton coming because of this interaction. Okay, let us now continue further. Let us see what is going to happen if you look at one proton coupled to three chemically equivalent protons. We look at one coupled to two protons, CH2. Now this CH is coupled to CH3 protons. Now let us see what happens. Now in this case, coupling 1 2, 1 3 and 1 4, they are all same. This is magnetically equivalent spin. Okay, all the three protons are same. Coupling to all other coupled proton is same. That's what our definition. Interestingly, here we are going to get a triplet for this. For this proton, here we are going to get a triplet. Something interesting. Now let us understand how that triplet will come. See this triplet, I'm sorry, how this quartet will come. Okay, for this proton, how this quartet will come. And this separation between adjacent transitions gives you coupling here. Similarly, in the triplet case, you get three lines. Adjacent transitions, if you select, measure the coupling, that will give you coupling between CH and CH2. Similarly here, if you take adjacent transitions, this is the coupling strength between CH3 and CH. You can take any of the adjacent transitions, this also doesn't matter. All the three are fine. Any of them if you want, you can take it. There is no problem. It will give you coupling strength. Now, how do you get this quartet? We developed triplet, right? Similarly, let us develop the quartet now. See how we get what is the intensity pattern? Remember, now I take single proton up to this coupled to two protons we knew. In the one of the previous example, we got triplet, right? 1:2:1 triplet. Up to this we have already done. So I don't need to repeat this. We will see what happens when it is coupled to third spin of equal strength. This was the intensity ratio when CH2 is coupled to CH, 1:2:1, 50, 25, 50, 25. Now, when it is coupled to this proton, we have to see that each of them will split into a doublet. This will split into a doublet. This will split into a doublet. This in 25 intensity, what happens? Splits into a doublet. This will become 12.5. This splits into 2. It will be 25 and 25. Okay, and of course this 12.5 is it. This will what happen? Split into 2. 12.5, 12.5. This splits into 2. So now what happens? Intensity is 12.5 here. This adds up. 25 plus 12.5 is going to be 37.5. This is 37.5, 12.5. Now what is the ratio of intensity? If you consider the ratio of the intensity between this and this together, this is 1:3. This, if you consider this as 1, this is 3 times. So 1:3 is to 3 is to 1. So in the quartet, you get intensity ratio as 1:3 is to 3 is to 1. Remember, when three equivalent protons are coupled to other proton, this proton will become a quadrat of intensity ratio 1331, and the adjacent peak, if you take measure that separation, this correspond to J coupling. Okay, that is the J coupling. Now, why this triplet comes? If you understand, there are three possible orientations, three spins you consider. Now we are dealing with three spins. This is all three beta, 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 all three alpha, alpha, alpha. Now there are two situations. Remember, we worked out once. It is one up, two down, one up. This is a situation two down and one up. This is a situation two up and one down. So there are three possibilities of equal strength, equal intensity. As a consequence, this is 3 times intensity. As a consequence, this is 3 times intensity. So we get, what are we going to get? We get a quadrat of intensity 1, 3, 3 and 1. You understood how I got a quadrat? Simple. You understand that this is three possibilities of equal intensity. This is three possibilities of equal intensity of orientation of the spins. So this is only one possibility. This is one possibility. As a consequence, 1331 is the intensity pattern for a quadrat. These are very important. When you want to analyze the NMR spectrum later, you must remember this is very important. Triplet pattern, quadrat pattern, doublet, all are, you should be in your fingertips to analyze. Now you understood. Let us now the same look at this proton. If I look at this proton coupled to this, what is the pattern you should get? It is coupled to only single proton. It means it will be a doublet because all are equivalent. This methyl group gives only a single peak and it is coupled to this proton and it will become a doublet. So for the entire molecule, if you consider, now what is the splitting pattern? This is a quadrat and this is a triplet. That is a splitting pattern for this molecule. And then intensity ratio is 1:3:3:1 and the adjacent peak separation gives you J coupling. Very simple. Now the intensity, every time I don't want to draw this family tree diagram and start understanding how the intensity comes. For this, intensity of the peaks of equivalent spins, when equivalent spins are coupled to other spin, it obeys what is called Pascal triangle. This is a Pascal triangle. Let us say I have a one single spin system. How many peaks I get? For example, CHCl3, if I see proton, I have already told you, we will get single peak. If I take two spins coupled, one spin coupled to another spin, each spin will be a doublet. So the observing spin will be a doublet like this. When one spin is coupled to two equivalent spins, n is equal to 2, then we are going to get, that is totally 3 spins are there. One is coupled to equivalent spins, we will get 1:2:1 intensity. If I consider 4 spins, one is coupled to 3 equivalent spins. Just now you worked out, it is going to be a 1:3:3:1 quadrat. Similarly, you can work out like this. Okay, this is called Pascal triangle. Pascal triangle simply gives you the intensity of the coupled proton when it is coupled to group of equivalent spins. Remember, group of equivalent spins will give splitting pattern to other proton, not that will split. Okay, so how do you generate this Pascal triangle? Very easy. You don't need to worry about anything. It is simple. First you write 1, below this you write 1 1, exactly just 1 at the center, on either side you write 1 1. What you do is, again write 1 here, take the sum of these two, 1 plus 1, add here 2, then write another 1 here. So now come here, write 1 here, add sum of these two, 1 plus 2, write 3, 1 plus 2, 3 and 1. So what you should do is, it always goes by the sum. Here 1, these two together will be 4, these three are 3 plus 3 is 6 and 1 plus 3 is 4, like that it goes. Okay, the splitting pattern, the way of generating this Pascal triangle is simply, all you have to do is, you have to go back and then see what you have to do. Just add the numbers, just above it two numbers and then write the sum here. This is the way you generate Pascal triangle. 1 plus 1 2, 2 plus 1 3, 3 3, 3 plus 3 6, 6 plus 4 10, like that you can generate. In principle, that is the simple easiest way, a school way of doing. But if you have already understood binomial expansion, what is this Pascal triangle number? It is nothing but the coefficients of the binomial expansion. Remember, you can write like combination. This is 0 C0. What is 0 C0? It is 1. It is nothing but A. Write simply A here. Okay. It is simply write A here. Okay. Now, when next one we write two hexagon I wrote here. Just hexagon is only for writing. Otherwise, you can write without that also. So now is 1 C0, 1 C1. Both are same. So now I'll take 2 C0, 2 C1 and 2 C2. 1 C0 and 1 C1 is nothing but coefficient, both are 1. It is like coefficient of A is 1, coefficient of B is 1. 2 C0, what is 2 C0? Coefficient is 1, this coefficient is 1 and central coefficient is 2. It is nothing but A plus B whole squared. Okay, when you take A plus B whole squared, A squared plus 2AB plus B squared. So the intensity is coefficients of this expansion. 1 is to 2 is to 1. Remember, this is easy to understand by looking at the coefficients. Come to this one. This is 3C0, 3C1, 3C2, 3C3. This is simple logic. You can keep on extending by the logic what is adopted here. This is 1, 3C1 is 3, 3C2 is 3, this is 1. So what does it mean? This is A plus B whole cube. A cube plus 3A squared B plus 3AB squared into B cube. What is the coefficient? 1, 3, 3 and 1. So this is a situation you get quadrant. Like that, this is A plus B whole to the power of 4, A plus B whole to the power of 5. Then you get the intensity here. I showed here 1, 5, 10, 10, 5, 1. So this is how intensities are generated in the Pascal triangle. So what I showed in the previous slide was simply addition, adding two numbers above. But mathematically, it is the coefficient of binomial expansion. Please remember that. Now let us understand more as far as the n number is concerned. When Pascal triangle for n equivalent coupled spins are present for spin of nuclei, how many transition you should get? But whatever you do, when one spin is coupled to n other spins, you must get 2 to the power of n transitions. Remember, this is what we understood when we understood family tree approach. If one is proton is coupled to other protons, 2 to the power of 2, you get 4 lines. When one is coupled to 3 protons, 2 cube, 8 lines. So we understood, A, B, AX, AMX spin system like that. So total number of lines will not change. It is always 2 to the power of n. But because some lines overlap at the center, like it became a triplet. Actually, how many lines were there? There are 4 lines. When 2 spins are coupled, one is coupled to 2 other spins, there must be 4 lines. There are 4 lines. Only thing is 2 lines are overlap at the center. Similarly, if you see here, one is coupled to 3 other things, how much you should get? 2 cube. 2 cube is 8. There must be 8 lines. But what happens? You get intensity 1, 3, 3, 1. 3 lines here are overlapped. 3 lines here are overlapped. And 3 plus 3, 1 plus 1, there are 8 lines. So number of lines do not change. The pattern appears triplet and quartet, etc. because some lines are overlapped because they have the same coupling and it appears as if we are observing less number of lines. In reality, these are 8 lines. So don't get confused. Now I'll understand this one. This gives you 2 peaks of equal intensity. This has 4 peaks, out of which 2 are overlapped. This gives you 8 peaks. This is 3, these 3 are overlapped. And what about this one? This will give you 16 peaks. Remember, this will give rise to 16 peaks, and out of which 4 peaks of this are overlapped, 6 are overlapped, and 4 of these are overlapped. In reality, it has 16 peaks. So now you should tell me what happens here. This has 32 peaks. These 10 peaks are overlapped here, 10 are overlapped here, 5 are overlapped here, 5 are overlapped here. That is 32. 10, 10, 20 plus 10, 30 plus 2. So 32 peaks. So the number of peaks always remains 2 to the power of n. Don't get confused. The pattern appears as triplet, quartet, etc. just because some of the lines overlap because of equal coupling strengths. This is what I wanted to tell you. Please remember this. Now we'll go further. So this already I explained to you. Now common splitting patterns in NMR we'll analyze now with this. Very interesting thing. Splitting pattern when a single proton is coupled to group of protons experiencing coupling with other protons or group of protons. Now a complex pattern we'll try to analyze. Okay, how we do that? We'll go ahead. Now splitting of a single proton coupled to other protons, we know that even A is coupled to X, it is a doublet. I started with the simple, then intensity is 1:1. Now 1 is coupled to 2 equivalent protons, A is coupled to CH2 protons, then CH will be a triplet, this is CH, triplet, and CH2 will be a doublet. Because CH2 comes at high field, remember, and this is a doublet because of this CH. Whereas this CH comes downfield, is a triplet because of this CH2. To understand the pattern, in this group, hypothetical molecule what I have taken here, CH2 will be a doublet, CH will be a triplet. 1:1, 1:1. Triplet, this is called doublet and a triplet. Of course, center of the triplet gives you the chemical sheet of this A, and center of this doublet gives you a chemical sheet of this. And the separation between these or any separation between adjacent these lines gives you J couplings. Now, CH proton is coupled to CH3. How does the spectrum come? CH3 comes in the high field region. So this CH3 will be a doublet because of the CH. Now this CH3 if you consider, this is going to be, this CH if you consider, this is going to be a quartet because of this one, see, of intensity 1331. Remember this one, CH will be a doublet, CH3 will be a doublet here, and CH will be a quartet in this coupled spin system. This is called doublet and a quartet. Again, center of this quartet gives you chemical shift, adjacent lines gives you J coupling, and center of this doublet gives you chemical shift of X, and this adjacent separation gives you J coupling. Now we will come to a situation. What happens when CH3 proton is coupled to a CH3 group? Hypothetical molecule I am writing. Now CH2 is coupled to CH3. What type of coupling you are going to expect now? What is the pattern? We will think carefully. There is no need to worry too much. Already we have worked out. This CH2 splits this into a triplet. This CH3 will split this into a quartet. So the spectrum should be like this. CH3 has to be a triplet and CH2 has to be a quartet. Very easy. You understand? CH2 is a quartet because of CH3 and CH3 is a triplet because of CH2. This is understandable. Again, how to measure the chemical shift, how to measure the J coupling is very well known. I have already discussed many times. Okay. Now, how do you measure? As already said, in an example like this, if you have taken separation between adjacent peaks, always gives you J coupling. If I take CH2 coupled to CH2, what is the type of pattern I expect? If X and Y are different, let us say there is no symmetry, then this will be a triplet because of this, and this will be a triplet because of this. Very interesting thing, right? So that's what happens. You get a triplet and a triplet in this molecule. This will give you J coupling, this will give you J coupling, and this gives you a chemical sheet of one. This will give you a chemical sheet of the other. Now we'll go further. Understand what happens to the splitting patterns when a single proton experiences coupling with many other chemical equivalent spins. Not one, many, let us say. Many groups of protons, groups of equivalent protons, if it couples, how does the splitting pattern come? You understand. Now, take a hypothetical molecule. A CH proton is coupled to CH proton, sorry, a CH proton here is coupled to another CH proton and a CH3 group. That means each group is experiencing coupling with two other groups. This is coupled to this and this is coupled to this and this is coupled to this and this. Let us see how the spectrum comes. This is a hypothetical molecule. And I am looking at this CH, highlighted one. Because this is my problem. Remember, my problem is this CH proton coupled to other two, CH and CH3. Now let us see how the pattern comes. We should immediately look at it and say, first, you have to find out what is the condition to look at the pattern. Whether JAX and JY are equal. If they are equal, there is one pattern. If they are different, there is another pattern. Now let us generate the situation for JAX equal to JAY. That means this coupling and this coupling are same. How does the spectrum come? Look at this pattern, proton. First it is going to be a singlet. Each line of this singlet will be split into a quartet because of CH3, and each line of the quartet splits into a doublet because of this. As I told you in one of the earlier slides, there are multiple coupling can be experienced by a single proton. So this proton experiences two types of coupling, one with the CH3 group, other with the CH group. So you understand now, and you get a pattern like this. It is called a pentet. 5 lanes are there. It's a pentet. What is the intensity pattern for this? 14641. Interesting. How do I know this intensity is 14641? We have to understand this. Let us generate the intensity pattern. Again, of course, I don't have to repeat again and again. Center of peak give you chemical shift, and all other peaks, separation of the adjacent will give you J coupling. Okay. Now, we'll generate the pentet pattern for you. How you get 14641 intensity? Very interesting. Let us see. First, A is going to split into a quartet because of CH3. That I have already explained to you. I don't have to repeat that. So 1331 intensity, it is a quartet. When one is ACH is coupled to CH3 is a quartet. Now this CH2 is coupled to this also. That means each line has to be a doublet. Each line. So now we will work out. Intensity 1331. Each will be a doublet. This will be a doublet. What is intensity now? 1 become 0.5, 0.5. What is this intensity? 3. Intensity should be 1.5 plus 1.5. Because the coupling is same, two lines here overlap. Okay? This line overlaps with this. Now this one. Again, intensity will be 1.5 plus 1.5 here. These two lines overlap. What about this one? This is intensity 0.5 and 0.5 because of this. We did not do any magic. We simply split the inner lines based on the splitting pattern. Whether it is one whole quartet is split into each and into a doublet because of this. We just divided each of the intensity by 2. Wherever it is overlapping now, we have to add up. What you will do is when you add up, what is the total intensity you will get? This is 0.5, this will be 2, this will be 3, this will be 2, this will be 0.5. What is this ratio? 1, 4, 6, 4, 1. It's a pentet. You understand? When you get a pentet in your spectrum, please understand there is a possibility this proton of your interest may be coupled to CH3 and also CH with the equal coupling strength. As a consequence, lines will overlap. It will be a quartet of a doublet. Lines will overlap and you get pentet of 1464 on intensity. Please remember this point very clearly. Now, if you will consider another situation, here we had a CH before in the previous molecule, you see, here we had a CH. Now I will introduce, instead of CH2, I will make this CH, I will make a CH2. Remember, here it was CH, now I am going to make it CH2. Again, JAX equal to JAY. What is the pattern I expect? Of course, first one you know, this is split into this by a quadrat. And each line of the quadrat splits into a triplet because of this, and you are going to get a sextet. Sextet of the intensity ratio 1:5:10:5:1. Okay? How do I know this? Very easy workout. You know, this splits this into a triplet, and each line of the triplet becomes a quadrat. And because of the equal coupling, some lines here overlap. So now it is, go back here. Let us say intensity is 1. When it splits into a triplet, I made all intensity such that total becomes 1. This is 0.125, 0.375, 375, 0.125. So the total is 1. Now this is 2. So it will become 0.375, 0.375, 0.1. Sorry, 0.25, 0.75, 0.75, 0.25. So that this total will be 2. Now the last one, same, it's a quadrat with intensity like this. You understand? Here 2 lines are overlapped, here 3 lines are overlapped, here 3 lines are overlapped, here 2 lines are overlapped, and is only single line, outer lines. Add up the intensity now. What is the intensity you are going to get? 0.125, 0.625, 1.25, 1.25 is 0.625, 0.125. Calculate the ratio. It is 1:5:10:10:5:1. Sextet ratio 1:5:10:10:5:1. You remember, this is the sextet ratio, I said. This is the sextet ratio, and this is what we generated here. So these are all the cases. I have taken example, hypothetical molecules. I have drawn the drawing for you to understand. In this situation, this coupling and these couplings are same. And now I did one trick here. I took proton A and took CH2 as the coupling with CH2 first. I took triplet and then worked out coupling with CH3 each of them and worked out the pattern and got a sextet like this. You may ask me a question. Why did I take CH2 first? Why not if I take CH3, what will happen? Will the coupling pattern is different? Let us see that. Now I'll take CH3 first. It is a quadrat, this one. Now what will happen? Each line of this quadrat will split into a triplet. Okay. Now add up the intensity. Same. There is no difference at all. Again, intensity is 1:5:10:10:5:1. What does it mean? The coupling pattern, splitting pattern is invariant with the order of coupling chosen for obtaining multiplicity. It is invariant. You take coupling of this to this first and then this later, or coupling to this first and then to this later. No problem at all. The order of coupling what you are going to take is immaterial. The final pattern remains same. You can work out the splitting pattern taking this coupling first and coupling to this later, or this coupling first and coupling to this later. Doesn't matter. The order of splitting remains invariant. Now I'll take another example. Here is a beautiful example. Again, hypothetical molecule. I have taken this proton A coupled to 2 CH3s have equivalent coupling. Understand? 2 CH3s have equivalent coupling. What is the pattern I expect? Doesn't matter whether you take this first or this first. Both are CH3s. It is going to be a septet. First pentet, sextet. Now I'm working out septet for you. 5-line pattern, 6-line pattern, now it's a 7-line pattern. See, count it. 1, 2, 3, 4, 5, 6, 7. this 7-line pattern is accepted. What is the intensity of this? 1, 6, 15, 20, 15, 6, 1. We can work out this one also, septet also in an easy way. How do you generate a septet? Now we have two CA3s. Each CA3 will first it will, this proton splits into a quartet, and each line of the quartet splits into another quartet. So now it's the first quartet, and each line will split into one quartet here, another quartet here, another quartet. I have given different colors and written the intensity. Now add up all the intensities the way I took it. A simple example I took. First I took this one quartet. I divided the intensity so that total become 1. Similarly, next one 3 is the intensity. I divided such that total become 1. Like that you do, and add up all the intensity. This is the ratio we are going to get. What is this ratio? 1, 6, 15, 20, 15, 6. This is a septet pattern. So when do you get septet? When one of the proton is coupled to two equivalent CA3 coupled groups with equal strength. Two CA3s of equal coupling will get a septet. So now so far you understood lot about coupling with how do you get the splitting pattern when one proton is coupled to a group of equivalent protons. Coupled, it could be CH2, one CH2, one CH3, or two CH2, or two CH3s, does not matter. We know how to work out the pattern, and we got several examples: a doublet, a triplet, a quartet, a pentet, hextet, and a septet. So many things we worked out. And these patterns you must remember when I analyze the spectrum. Now soon I will start the analysis of the spectrum of simple molecules, reasonably complex molecules, where you have to learn the analysis easily. At that time, all these things are required, this information. Looking at the pattern, you must save the pentet or a sextet or a septet. This helps you. Intensity pattern, the multiplicity. Okay. So this is what it is. Next, we will take some examples of splitting pattern of a proton coupled to protons or group of protons with different coupling strength. Very important point. Remember, so far I was taking here, for example, here JAX equal to JAY. They were all equal coupling strength I took. In the other molecule also, CH2, CH3, they were all equal strengths. Now what happens if the coupling strengths are different? It's not same. How does the pattern change? Okay, we will start this with a simple example. What happens when CH is split by CH and CH2? This is a hypothetical molecule. A CH is split by CH and another CH2. So now you see JAY is greater than JAX. This is close by. This is only 2 bond coupling. This is 1, 2, 3, 4 bond coupling is much smaller. So AX is smaller than AY. Couplings are not same. They are different couplings. Now see the pattern. When it split by this proton, A is split by Y, it is going to be a doublet. Now what happens? Each line of this doublet is split into triplet by CH2 proton. Okay? You understand? This is what happens. Now, I did not write explicitly one below the other. First it was a doublet, and each line was with it. First it was a doublet, and each line is split into a triplet. I wrote on the same diagram so that we are going to get a pattern like this. There is a way to name it. Which is the largest strength here? JAY is larger than JAX. What do you call this? It is called doublet of triplets. First, largest coupling you have to say. Largest coupling is a doublet. And each line of the doublet becomes triplets. What is the triplet separation? Triplet coupling is small. So smaller coupling comes second. Largest coupling comes first. So you should call it as doublet of triplets. That is the nomenclature. Don't forget that. You have to use the nomenclature. It is a doublet of a triplet. And again, center will give you a chemical shift of this, and this largest separation here gives you this coupling, and each line of this splits into a triplet, and the adjacent lines of the separation here gives you this coupling. This large coupling gives you AY coupling. Now what is the pattern for the Y proton? Another interesting thing, I looked at A. If I look at Y, what will happen? Now in this case again, JXY is very much smaller than AX. Now it is a doublet Y proton. First, which is the largest coupling? JXY. It should be not AX, it should have been AY. Okay, doesn't matter. So one of the coupling, AY splits into a doublet because of this A. It is a large coupling, JAY. Then each of them splits into a triplet with a small coupling. See, far away. 1, 2, 3, 4 bonds away. This coupling, YX coupling, is small. This should be YX. Now, pattern remains same. Only thing is, these lines are close by because coupling is smaller, this one. But what do you call this pattern? This is also doublet of triplets. But only thing is, here the triplet separation is larger because this coupling is more. Here this triplet separation is smaller because this coupling is small. But the pattern is called doublet of triplets. You understand? So now in this class we try to discuss more about the multiplicity pattern when one proton is coupled to equivalent spins of identical couplings, equivalent groups of spins, and also we took one or two examples of couplings which are spins where the coupling strengths are not equivalent, and we generated this pattern called doublet of triplets. And if I observe one proton and other proton, how the spectrum changes we know. And this nomenclature always, first coupling, largest coupling you have to say first. Largest coupling is doublet, then smaller coupling here is the triplet. So such type of patterns like this, simply look at this coupling is larger and this is smaller, it is called doublet of triplets. So we can generate like this for few more examples where the complex multiplicity pattern to analyze the spectrum will become easy. And I will stop here today. In the next class we will discuss much more and we will start analyzing.